Hello everyone, this is Niteen Mohod, and here through this video we are going to learn the Boolean laws, which are very important in digital electronics for solving the different Boolean equations. Boolean laws, there are varied types of Boolean laws and we are going to study them so that the logical expression can be solved by using these laws. So first we are going to see what the AND laws are. Now AND laws are derived from AND gate operation and hence the name is. The four AND laws are as follows. Now if you are remembering the AND operation, in AND operation for both the high inputs we were getting output 1 in a 2 input AND gate, while if any one of the input is 0 or when all the inputs are 0 the output was 0. So keeping that in mind, these four laws are derived from the AND operation and hence called as the AND laws. So first is A dot 0 or A and 0 equals to 0. Now A dot 0 means if one of the input, which we don't know what it is, whether it is 1 or whether it is 0, but second input is confirmed it is 0. So if one input of AND gate is 0, whatever may be the second input is, the output has to be 0. So this is the first AND law. Second AND law. Now here A into 1 or A and 1 equals to A. Now it entirely depends upon the value of A, whether it is 1 or whether it is 0. If it is 1, then 1 into 1, 1 means you will get same. If it is 0, then you will get 0 here. Then A into A equals to A means it is again going to depend upon only the value of variable. If it is 1, 1 into 1, 1. If it is 0, 0 into 0, 0. And when we are talking of the last AND law, that is A dot A bar or A and A bar. Now if the variable is given and its complement is given, means if variable is having value 1, the complement has to be 0. So 1 into 0 you will get 0. If this variable is 0, complement will be 1. So 0 into 1, 0. Means in totality all these laws are following the AND operation. I hope these are clear to you. Then OR laws. As we have seen, the AND laws are derived from the AND operation. Similarly, the OR laws are derived from the OR operation and hence the name is given. There are again four laws for the OR laws. So A plus 0. Now A plus 0 means A or 0 you can say. When one of the input of OR gate is 0, so at that time it will entirely depend upon the second input what it is. If it is 1, this has to be 1. If it is 0, this has to be 0. So that's why we are written here A. When A plus 1, you will always get 1 because one of the input of OR gate is 1. So you need not require to consider the position of second input, whether it is 0 or whether it is 1. In all cases, 0 plus 1 will be 1 and 1 plus 1 is also 1. When A plus A is there, you always get A because it always depends upon whether it is 0 or whether it is 1. So 0 plus 0, 0 and 1 plus 1, 1. And when we are talking about the last OR law, that is A plus A bar, that is if variable is 0, complement has to be 1, and when this is 1, complement has to be 0. Means any one of the input of this out of these two will be 1. So naturally output will also be 1. Then commutative law. Order of variable in AND and OR operation is insignificant or not important, that is does not make any change to the result. So A plus B can be written as B plus A. Similarly, A and B can be written as B and A, or A dot B can be written as B dot A. This is commutative law. Then associative law. Any two terms of sum or any two factors of product can be grouped as, so you can see here A plus B plus C can be written as A plus B plus C, and similarly in a factor of product you can say A dot B dot C can be equivalently written as A dot B dot C. Then distributive law. Factoring or multiplication of different terms in a given expression is allowed, that is A dot B plus C can be written as A dot B plus A dot C. Similarly, A plus B dot C can be written as A plus B dot A plus C. Similarly, A plus A bar B, that is A bar dot B, can be written as A plus B. So these are the standard formulas actually, and which holds true for left hand side and right hand side. Then law of complementation. So complementation means inversion, that is 1 converting into 0 and 0 converting into 1. This law is derived from the NOT gate because it's a basically NOT gate operation. According to this law, A double bar equals to A. If A equal to 0, 0's bar will be 1 and 1's bar will be 0. So 0 you will get 0, 1 will be, you will get 1. Then Demorgan's theorems. There are two Demorgan theorems. Demorgan's first theorem. So here the statement of Demorgan's first theorem is complement of sum is equal to the product of complements. Logically it is written as A plus B whole bar equals to A bar dot B bar. Logic circuit equivalence for this expression can be shown like this. Here we have shown two input OR gate having inputs A and B. So output of OR gate will be A plus B, and A plus B working as a single input for NOT gate. So output will be A plus B whole bar. This is equivalent to the right hand side of the Demorgan's first theorem, that is A bar dot B bar. So A through NOT gate, when passed we get A bar. Similarly B will be converted to B bar. Now A bar and B bar will be the inputs for AND gate. So output of it will be A bar dot B bar. The truth table for the left hand side and right hand side of the expression is shown here. Since two input gate is considered, two variables are considered in a theorem, we are using here two inputs A and B as a variable, and there will be four conditions, that 0, 0, 0, 1, 1, 0 and 1, 1. So for the left hand side, that is A plus B whole bar, suppose both the inputs are 0, A and B. So A plus B, that is 0 plus 0 will be 0 and 0's bar will be 1. So I will get 1 here. On the right hand side, A bar means 0's bar, that is 1. Again 0's bar means 1 and 1 into 1, I will get 1. So left hand side matches right hand side. Similarly, you can go for all the conditions and all these conditions will hold true. Moving on to the second Demorgan's theorem, and its statement is complement of product is equal to the sum of complements. Logically it is written as A dot B whole bar equals to A bar plus B bar. Logical circuit equivalence for the equation is shown like this. Here, since it is A dot B whole bar, we have taken here initially AND gate with two inputs A and B. The output will be A dot B, which will be an input for NOT gate. So the output of NOT gate will be A dot B whole bar. For right hand side, A bar plus B bar, A will be converted to A bar through NOT gate, B will be converted to B bar through another NOT gate, and this will, A bar and B bar will work as an input for the OR gate. So at the output of the OR gate, you will get A bar plus B bar. Again, the truth table for the left hand side and right hand side outputs we have shown here. Again, there will be four conditions, 0, 0, 0, 1, 1, 0 and 1, 1. We will see one condition. So A dot B whole bar. So 0 into 0, that is 0, and 0's bar will be 1. So for 0, 0 you will get here 1. For here for 0, 0, 0's bar will be 1, and here also 0's bar will be 1. But 1 plus 1 is 1. Similarly, we can go for one more condition. Now A 0 and B is 1. So A dot B whole bar. So A dot B means 0 into 1, 0, and 0's bar will be 1. So we are getting 1 here. And here 0's bar will be 1 and 1's bar will be 0. So 1 plus 0, that gives me 1. Similarly, you can go for all the conditions and you will find that the left hand side matches the right hand side. So I hope the different Boolean laws like AND laws, OR laws, commutative law, associative law, distributive law, along with the De Morgan's first theorem and second theorem are clear to you. Thank you.